Hey, all students. All right. Hope you're working through these and working well. Here's number 48. That was I guess, the fifth of my sixth one on my list. I said I would do and went ahead and printed a hard copy here. But it says here, a heat engine operates between two reservoirs. Here's the hot one and here's the cold one. So if I make a little thermodynamics diagram of my engine, I would say that up here we have 600 Kelvin, and it brings in energy, so QH, and for that matter, it also brings in some entropy. The engine does some work, but as we've said in a couple of these other examples, because of the entropy has to exit. And fortunately, the entropy can be more concentrated, if you will, or you can get more entropy at a lower temperature. So you don't have to have as much energy exiting to the lower temperature to justify the same entropy. And so because of that, the cold could be less than the hot, and the difference between that is now available to do work. And so that's kind of how we did our heat engines here, and how we kind of were discussing how the entropy is kind of a measurement of the energy that is not available to do work. That was the original Clausius definition here of entropy before the microscopic view gave it more of a description of random or disorderedness, which, as I mentioned, I'm not always a big fan of the phrase disordered, because, what is disordered in the eye of one beholder might be different. A rose by any other name might smell as sweet. And some people are allergic to roses. And you give them a rose to smell, and they start sneezing for the next 10 minutes, and they don't like that smell. So it is in the eye of the beholder a little bit. I think the example I gave was kind of the mixing of salt and water. To me, you put salt and water, you had two clumps of different substances, and now you have one solid or one liquid, and it's all clear and looks uniform. To me, that looks more organized. But in reality, on a microscopic level, you've got an intermixing of them, and so it's disorganized. So that's why I said the disorganized is probably not a good microscopic word for entropy. That's why the more probable state is. That's a much better word, because that's really what's going on. It's the most probable, not so much the most disorganized. Although disorganized works well. It does. Now, that aside, let's work on this one. And I think this does have some entropy in there. I know the other ones, the earlier problems, didn't have any entropy. Yeah, so somewhere down here he's talking about entropy. So good. I'm glad I kind of put this in my little model here. But let me come back to the question. So the heat engine operates between a 600 and a 350. It takes in 1,000 joules of energy from the high temperature reservoir. Okay, so this is going to be 1,000. Does it say per second or per hour or anything like that? Is it a rate? No, just, okay, so in some time frame, which we're not told, it gets 1,000 joules of energy from the hot reservoir. And assuming the same time period, it performs 250 joules of work. So this coming out here is 250. And so I think indirectly they're making us use conservation of energy. That is the first law of thermodynamics, to say then the heat coming out must be 750. So that 1,000 comes in. We need to have 750 come out to then deal with the entropy, and then we've got 250. Okay. So we finally get to the question. Find A. What is the entropy exchanged of the universe in this process? Okay. So the engine goes through a cycle. They don't really say what the cycle is. I suppose it could be a process where it did the work by expanding, or no, warming, no expansion yet, by constant volume and expanding at constant pressure. So there's where the important work done of the engine goes. And then we've got to return it, so maybe we lower the pressure at a constant volume by some kind of cooling process, and then also a cooling process, but shrinking its volume, so negative work on the engine. And so maybe this is the cycle, who knows, just to do something a little bit different. It could be the classic Carnot cycle. It could be different color here. We did the Otto cycle, where we'd have like a small volume and a big volume, and so it would go adiabatically, isovolumetric, adiabatic, isovolumetric, and return. And so we'd have that blue diagram. It could be the diesel cycle. I don't have another color nearby, but a diesel cycle is kind of starts off like the Otto cycle, adiabatic, but it's more adiabatic, has a higher compression ratio. And then you do a direct injection of the fuel, so the fuel ejects it, keeps it burning, and if the burns too much, the pressure goes up, the fuel is kind of hindered from going in. But if the burning's not enough, the pressure drops, and so it kind of follows kind of a constant pressure for a little bit. Then the fuel cuts off and it expands adiabatically, and then the exhaust valve opens up. Anyways, and so this would kind of be the diesel cycle. I don't think we got a chance to talk about that one in class, but I think there's a homework problem then on it that you saw. Anyways, my point is that I guess I just kind of wanted to review a couple of cycles that we talked about. But more importantly, if it is a full cycle, the change of any of your state functions, so that's the change of internal energy, that's the change of the entropy, that's the change of pressure, that's the change of volume, that's the change of temperature, all of these would be 0. You would end up exactly where you started. So whatever the cycle is of this engine, which is not told, we know that when it gets back to where it started, wherever you were looking at the cycle, it has the same temperature, or it has the same volume, or it has the same pressure. And more importantly, for this case, is it has the same entropy. It also has the same internal energy. Now, the Q and the W, which we don't usually write as a delta, they always are, those are not necessarily 0. Those are path dependent and would be heavily determined by which of the paths we take. If I can do a little mini lecture review here in this one. But again, the focus for this problem is right here. So the change of entropy of the engine, even though we don't know its cycle, we know its change is 0. And if they had asked what the change of the engine is, we could just say 0 and be done. But they asked for the change of the universe, I believe. Find the entropy change of the entire universe in this process. So we have to include not just the engine, which is the easy one, but we also have to include the surroundings. And the surroundings, and I'll do it 2 calculations, because there is an exchange of energy right here where it comes out of the hot environment and into the engine. And so while the entropy is going into the engine, which, as we said, then comes out of the engine, so right here, these two are equal, that's why the change of entropy is 0 for the engine, that doesn't necessarily mean the loss of entropy when the energy comes out of the surroundings into the engine, and the gain of entropy of the surroundings when it goes from the engine into the surroundings are the same. And so the net result might be a change of entropy. Now, if it was a Carnot cycle, we know that the surroundings would also be 0, because that was our justification to saying that the Carnot cycle is the most perfect case, that you can't do better than it. But I have a feeling that this is not a Carnot cycle. I have a feeling that we are going to have a increase of the entropy in the surroundings, even though the engine is zero, and so the whole universe has an increase, and this is not a reversible process, and it is not at the maximum Carnot efficiency. So in my surroundings, I will do an integral of dq over t, and I will kind of imply that the environment out here is staying at 600. And so this hot reservoir that they're talking about, as it's putting energy in, is staying at 600. It's either so big that the energy that goes in here, these 1,000 joules, are kind of just minor compared to this whole thing. So we can say that it really didn't change its temperature. And so while as we put energy in, maybe this did change its temperature, the reservoir did not. And so my surrounding calculations, I will be, doing something like this, just to maybe comment on what we did in the last example. Here it is, number 36. We had the coffee and the cream, and we said the temperature does change, and so we got this formula for the change of entropy after we did the integral. Here, we're going to just simply get a Q over a T. And that showed up in one of the earlier ones. That real long one, I guess that long one was, what number was that? It was like number 20. And it didn't really ask for entropy, but I worked it out. Anyways, so let's do the surroundings, and I'll just say that for both the surroundings, whether it's the energy coming from the environment into the engine or from the engine into the environment, I'm going to say that the environments, they kept the same temperature. So the hot reservoir kept its same temperature, and the cold reservoir kept its same temperature. And so the calculation is the same. And in this case, the energy comes out of the hot reservoir, and that's where I'm going to put a negative 1,000 here. And the temperature is 600 Kelvin. And so this is a 10 over a 6, which is 1 and 2/3. So 1 point, I'll call it 67 joule Kelvin. Oh, and negative. So that's the decrease of the molecular motion because of the energy coming out of the hot reservoir. Okay, now going in to the environment coming from the engine would be a plus 750 joules. So less energy. Again, that's why we have some available to do work. But because it is at a lower temperature, this can actually represent a larger amount of entropy than what went out of the environment. And so let me grab a calculator for this. And so this is 750 divided by 350. Yeah, and so this is a plus 2.14 joule Kelvin. And so when I put these two together, I will have a net change of positive. And as we said, according to the second law of thermodynamics, it would only be possible if this was either an increase or equal to 0, but never a decrease. And so I guess we would have to say that this engine is operating at something less than the efficiency, the perfect Carnot efficiency, but not bad. In fact, maybe I hope the question goes on to talk about this a little bit more, and I think it does. So let me move this out of the way and come back to the question. So we did A, the entropy change of the universe in this process, and then B, the work that could have been done during by an ideal Carnot operating between these two reservoirs. So if I just did a quick calculation for what the efficiency could have been, and I'll just say what it really is 250 out of the 1,000 we put in, and that's a 1/4, 0.25. So this engine's operating at a 1/4 efficiency, but it could be operating at, let's see, the cold temperature is 350 and the high temperature is 600. So 1 minus 350 over 600. So it could be operating at about a 41%. So I guess more. Just shut my door. It's getting kind of noisy here in my place, and I didn't want you to hear all that. Okay, so this is what it could be, which meant if we then looked at a Carnot efficiency and said work compared to the heat put in, and then this being 1,000 and the Carnot efficiency being 417, this is how much work could get. And so, again, as an engineer or a scientist, we'd be shooting for this. And so looking at our engine as described, we're saying, okay, we're getting 250. That's great. And we know we would never get 1,000. But it's quite possible we can get 417. So, you know, maybe this would be nice if we can get this into the 300s. I mean, it seems like if we put a little more effort and money into it, we can get 300 or 350. Yeah, it would cost more, but we're going to get a lot more out of it. So maybe it's cost effective. If this was already at 400, I probably wouldn't shoot for 417 from a business point of view. I just said, weigh all that stuff and all that hard work we're going to do, and we're only going to gain, 17 joules. That's just not cost effective. Okay, now here is where I'm glad the author asked this next question. It says, show that the difference between the amount of work done in parts A and part B is equal to this. Okay, so let's just talk about how much work we could have gotten out for 17 and how much we did get out. Okay, and so if I take my 417 and subtract my 250, well, you might say that we missed getting 167 joules out. And we lost that, and now it's not available anymore. And so this is trying to say it went into the entropy. That's where the entropy increased. And so if we take this, and so we take the temperature of 350, and we multiply it by 0.473, and let me put Kelvin, and let me put joule over Kelvin. This might give you some kind of feeling and understanding of then what the entropy is. Entropy now is that measure of that lost ability to do work. It's energy that's not available anymore. See, so now that we didn't do it with the highest of efficiency, we've lost that. And we lost how much? Well, that's what the universe is, the entropy of the universe is trying to indicate on our calculation. All right, so if I put this all together, other than maybe some rounding here, this is 166 joules. And so notice that's what it's trying to say here. And so, again, that entropy is a good way of measuring the energy that's unavailable to do work. All right. Well, hope that one was kind of insightful and helpful also. Take care.